Okay, so I have begun the recording for today's topic, which is on sequence. This is a new topic, which is slightly different than the other topics that we have covered. Just to remind you, we have another topic, which is, I think, topic number 8 on techniques of integration, or topic 9. So these are the topic that I have not, and I'm not going to cover in live lecture, but it will be on the shape of, it will be conveyed in the form of a micro credential. However, I understand that the learning space in the USM is not accessible. So I will try to move it into YouTube so that the same content could be also accessed. Okay, so sorry about that. I have to transfer, but I have to take time. I'm currently very busy at the moment. Hopefully after this week, I'll be free to make the transfer. So you could then have an easy access to this micro credential format. I think it's easier for micro credential for you to learn because the time of the video lectures is about 10 minutes, so it would not be so taxing. So you can take your own sweet time to go through the module one by one in time. But for the moment, we will be going to the next topic, which is on sequence. Now, the sequence and series topic is the last topic to be covered. In case we do not able to cover this, then I'll use a previous recording as a substitute, especially towards this time of the year. We're heading to the end of the semester, and then we are going to have a long holiday, the Chinese New Year holiday. So I'll make some special arrangement. Maybe we'll skip some class or something like that. But be reminded that there will be a test, right? So there will be a test next week. So be prepared for that. The test will be still on, and you have to prepare for your test. I think the test will teach up to the last chapter, last topic where we stop. Okay. So I have not prepared the test yet, but I'm going to do it very soon. I'm still waiting for people to come in. Maybe like only 1/10 of the people are here. But anyway, I'll continue with my lecture for the sequence. Now, sequence is different than function, but in a way, sequence can also be considered as very similar to functions. Especially important in the idea of sequence is first we have to define what sequence is. Then after we have defined what sequence is, then the most important thing in this topic of sequence is to calculate or to determine the limit of the sequence. When I say the limit of a sequence, we mean we want to know whether the sequence converges or not. And if it converges, then what is the value it converges to? So this is very similar to a function. I give a function and ask you at a point where the limit of the function at that point converges or not. That is, the limit at that point exists or not. But in the sequence case, the limit is taken at infinity. So usually we will ask the questions, the limit of sequence, what it is, if it exists, then what is the values of it? And the limit of this is taken when n goes to infinity. This is similar to the case where I give the function, ask you whether the function converges or not when x tends towards positive infinity. Right? So in functions, we ask the questions whether the limit at infinity exists or not. If it exists, then what is its limit? So in this topic of sequence, we define new mathematical object, which is very similar to function, but not exactly the same. The sequence that we are going to talk about here is sort of like discrete. It's very different from function in the sense that function usually is continuous. So when you represent a function on xy plane, you draw a curve to represent a function like this. So this is x, and this is the value of f. Then the function represented to be like this, and x range from some number to some number continuously. However, for a sequence, the sequence is discrete. It's described by a terminology called an. So an is then usually used to describe the terms in a sequence, and you describe a sequence using this terminology. So in the case of a function, we use fx to define the function. So in this case, the values of the function is f. Here, the values of a sequence is defined as uh, an, and this an is what we call the term in a sequence, and is placed inside an curly bracket. The curly bracket here refers to a set. A set is like a container that contains elements in it. So an in the curly bracket represents a collections of infinite terms, but each of the terms in the sequence is denoted by a0, a1, a2, a3, etc. up to a to infinity. Okay, so every single value of the sequence is given by an. So in this case, an plays the role of the values of the function. If you compare a sequence to a function, a sequence changes from one n to another. So in this sense, the n, which is called the index of a sequence, plays the role of x in the function. Right? So for a function, when x changes from one number to another number, the values of the function f changes. So in this case, a sequence has what we call a term of an. So an is the term, the n term. N is called the index. So this n changes from 0 to 1 to 2 to 3 to 4. So in this sense, the index plays the role of x. However, for a sequence, the variable, not the variable, the number n here is discrete. Unlike the case of a function, x is a continuous number. Okay, so if you want to make comparisons, that is how you compare. Imagine the term an, the term an is corresponds to the values of y in the function, where y is the function itself evaluated at x. Where x is what we call the independent variable in a function, and the independent variable x in a function corresponds to the index of n in an sequence. And the n in the sequence takes only discrete number 0, 1, 2, 3, 4, 5, whereas x is continuous. However, it's always possible to map a sequence to a function. Right? You just make sure that you define a function such that the values of the function at some number n in discrete number, f at 0, f at 1, f at 2, f at 3, equals to the values of the sequence term an. So in that sense, you can then couple a sequence to a function. But I would like to remind you, when we talk about a sequence in this topic, it should be considered as just a sequence. It is not a function. Right? Sequence is sequence, function is function. However, you can always create a function to tie up with a sequence. Right? But still, we are still looking at sequence. We want to ask the question of, given a sequence, what is its limit? That is, when n goes to infinity, then what is the values of the sequence? Okay, so this is the terminology that you should know when we talk about a sequence. A1, A2, A3, A4. Each term is represented by an, and this an is called a term. I think this A here is a term. So each term is indexed by a number called n. Okay, so the n here in the sequence, in the term of a sequence, is the index. In general, we describe the sequence in the form of a curly bracket. So there is an underscore of n here. Okay. So usually the sequence is described by some simple formula in terms of n. It's just like when you have a function, you describe a function f in terms of some operation performed on the variable x. Say, for example, fx equals to x squared, or fx equals to 2x plus 3. So you describe different types of function by using different formula. Likewise, a sequence is expressed in terms of n. Say I give you a sequence. I say the sequence term an is equals to 2n. Then immediately you know what the sequence looks like. That is, This an is given by a set of number, where each number is 2, 4, 6, blah blah blah. So here, if an is equals to 2n, I have to call out my whiteboard. So in this case, if an sequence is given as an, then you can explicitly write down the uh, the sequence. Say you have an equals to 2n, then the sequence is written as this, and it is a collection of a number in a set. The curly bracket, as I mentioned, is a container. It's a set. Set is just a container that contains many elements. The numbers of elements in a set could be finite or could be infinite. And in this case of a sequence, the order of the element in the sequence is important. Say, for example, when you write down this one, it's understood that the first element in the sequence is denoted as 0, 1, 2, up to infinity. Is A0, A1, A2, A3, up to infinity, and it won't stop. Okay, so the sequence index is usually range from 0 to infinity. Then you should be able to fill up the content of the elements or the content of the sequence, A0, A1, A2, term by term. So here A0 is just 0. The first term is A0. The second term is A1. So A1 is just 2. The third term, so this is the first term, the second term, the third term. Maybe I should rename the way how I name the sequence. So I will call the first term here, not the first term. I should call it a zeroth term, right? Because zeroth term is indexed by n equals to 0. The first term is indexed by n equals to 1. Then the second term is indexed by n equals to 2. So the sequence has a zeroth term, first term, second term, third term. And be reminded that the very first term in the sequence is indexed by n equals to 0. And I'll call this first term the zeroth term by referring to n. That will avoid a lot of confusion, because last time we used it, okay, the first term, second term, third term. So when I say the first term, I'm actually referring to A0. When I say the second term, I'm referring to A2. So that was actually quite sometimes confusing. But if I change my way of referring to this term, I call the zeroth term. Then you know I'm referring to A0. Then the A0 or the zeroth term is the first term in a sequence. So you fill up the zeroth term in the sequence, the first term, the second term, the zeroth term, first term, second term, third term, fourth term, etc., up to the n term in general. Then the values of the n term is 2n. Then it goes all the way up to infinity. So this is an example of a sequence. I have to introduce a sequence in a slightly more elaborate manner so that you understand better how a sequence looks like. Because the way how the sequence is defined is slightly different than the way how the function is defined. Okay, so this is about the sequence, and the sequence has the order where the terms in the sequence appears is important. Therefore, this sequence and this sequence will look very different. So up to this point, I hope that next time you understand what you mean by a sequence. Okay, a sequence is just a collection of terms in a set where each term is described by an, and an is usually expressed in the form of n. Right? So n could change from 0 up to infinity, and n should be an integer. So the idea of a sequence is actually not that difficult. And the sequence should be understood that it's sort of like be represented on the graph in a discrete manner. So you represent each term in the sequence either along the x-axis, or you plot it on the xy plane. Well, in this case, it's not an xy plane. The y-axis represents the values of an term, and the x-axis, the y-axis represents an, and the horizontal axis represents the values of the index n. And index n begins from 1, then it goes to 2, 3. So the values of an is represented by the values in the vertical axis. So you either represent the sequence in this manner, or sometimes you represent the sequence on the x-axis. So the values where the point sits on the x-axis represent the values of the term an. And then you have to label the term point by point. A0 is this point, A1 is this point, A2 is this point, A3 is this point, etc. Now let me be a little bit careful when I talk about the way how the sequence is defined. Yeah, I think okay, so I might be not entirely correct when I say that the n should begin from 0. So it looks like here the n begins from 1 instead of from 0. So I maybe have to make the changes to what I had said a minute ago when I defined a sequence. I said a sequence begins with an index n0. That is what I said here. But I think this is not necessary. Sometimes, I think most of the time, according to this, the n actually begins from 1 instead of beginning from 0. Okay, so I have to make these slight corrections to define the values of the index n in a sequence. It is not beginning from 0, but it beginning from 1. However, the difference is minor. So, so this is not true. This is not. So in this case, it's not true. So for a sequence that is given by this, then this is the sequence beginning from A1. Therefore, so the first the zeroth term, 0 has to be omitted. So the sequence beginning from the first term. So this is an example that is given here. So it's consistent with the definition that the index in the sequence begin from 1 instead of beginning from 0. However, as I mentioned, the difference is actually very minor. So say this is the sequence of an given by the term an equals to square root of n, and this is the bn in terms of bn equals to 1 over n multiplied by a factor of -1 or +1, depend on the values of the index n. So for some n, it is positive. For the next n is negative. So this is a sequence that is one. The first term is positive in sign, second term negative sign, third term positive sign. So this is called what is called an alternating sequence, where the sequence value alternate in the sign, positive, negative, positive, negative, positive, negative. Then Cn is another example. So you can label or write down all the terms of Cn term by term. For Cn equals to n equals to 1, n equals to 2, n equals to 3. So given any sequence, it should be easy to work out the values of the terms quite easily and write down this. So another example is this. This is a sequence that is either +1 or -1. So this is also considered as a sequence. So you represent a sequence on either this manner or this manner. So if you represent the sequence using an x-axis, then the values on the x-axis represent the values of the sequence. And for each of the point that you label on the x-axis, you have to label the sequence number n. So this is n equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5. So when a sequence converges, then you can actually sort of like see the conversion of a sequence from a graph like this. Like this is very similar to a function, right? So if I say if a function of fx converges to a limit when x goes to infinity, what you expect is there will be some horizontal asymptote where the function will converge to this number either from the left or from the right. So by looking at the shape of a function at very large x, you can imagine that this function converges to that number. Similarly, for the case of a sequence, so if a sequence, if you label it onto the an versus n axis, and each of the point here seems to go down to some constant number, then you intuitively understand that the sequence converges to a number. But for the case where you represent the sequence on the x-axis alone, then it would be like, say if this is the x-axis, say you say this is the first term, a1, and the second term is say a2, then third term is like a3. So this is like x-axis, right? So then this term maybe, say for example, it could be like 2, it could be like 2.2, 2.3. Then you could have the third term, say a4, which is 2.31, blah, blah, blah. So if these functions, or if this sequence converges, then I can imagine that the points that is representing the term in the sequence will get closer and closer up to some number, L, where when you go to higher and higher n, then the distance between one point to another point on the x-axis that represents the an will become closer and closer. Then all these points initially discrete would then seem to all cluster into a single region where the distance between the point and point will become closer and closer and closer. That is how you can imagine a sequence converges. Okay, so when a sequence converges, then we want to know what is its value. So the important thing in this topic we're going to spend next couple of minutes to explain is to find out the limit of a sequence. Right? So in order to find out the limits of the sequence, such as this one, you can actually see quite well that for example, Cn, the sequence seems to be, well, it's not that easy to see the sequence of Cn. Maybe we look at a sequence like maybe like this. Say if you have a sequence an which is equal to 1 over n, then you know that the sequence would be going like 1 second, 1/3, 1/4, and it goes to all the way up to. So if you represent this sequence in an axis of an over n, then you start out with 1 here, then you can see quite well that finally the sequence will converge to 0. So we said the limit of the an when n goes to infinity is 0. So that represents the limit of a sequence. Right? So sometimes we don't write this in this way. We just say an converges to 0. So this is the same as writing an n goes to infinity equals to 0. So there are two ways of writing the limit of a sequence. If it exists and limit, then the limit L is an finite number. But there could be also possibility that a sequence does not converge. For example, an equals to say 2n, then this would be a sequence of the form 2, 4, 6, blah blah blah. And if you plot this sequence on an axis, then you expect the number or the sequence to be going point by point up to infinity. And in this case, the sequence has no limit. It does not converge. So when a sequence converges, we say the limit of the sequence exists. If the sequence does not converge, then we say the limit of a sequence does not converge. Does not exist. So we are going to learn two theorems, a few theorems, theorem 1, theorem 3, and theorem 4, and theorem 5. So all these theorems are meant to be the tools that will help us to determine what the limit of a sequence is. Right? So this is the purpose of learning all these tools. So you can understand that the whole topic is devoted to calculate the limit of a sequence if it exists. Then it shows the knowledge of whether a sequence converges or not is very important, because you have the whole chapter telling you how to do that. This is very similar to when we study the limit of a function. Right? So we spend a lot of time to also try to work out how to determine if the limit of a function exists. If it exists, then what values of it is, right? So this is very similar, but the techniques to determine the limit of a sequence could be slightly different than the way how we determine the limit of an function in the limit where x goes to infinity. However, the tricks that we are going to use, theorem 1 to theorem 2, theorem 5, is like this. The tricks is very similar. It's two types of tricks. The first type of tricks is to tie the sequence to some invented function. As I mentioned, sequence and function are two different things. So we are already dealing with sequence. We ask the limit of a sequence. In order to determine the limit of a sequence, we have to invent a function that somehow is tied to the sequence, at least at the point where n is discrete. Then you make use of the limiting properties of the function to help you to pin down the limit of a sequence. Right? So this is very usually applied in mathematics as well as physics. You want to prove something that exists here, which is very difficult to prove in mathematics. You go to the heaven or you go to other space and prove it there. Then you come back here because it's easier to prove it there. Right? So here to find the limit of a sequence, you go to the function space and use the tricks that you have learned to determine the limit of the function there and prove that the limit of the function there when x goes to infinity exists. Then you translate the result back to the case of a sequence. Then you can, by this manner, you can determine the limit of a sequence. Right? So this happens very often. I think in superstrings also like that. In order to calculate whether the universe exists or the time now is whatever, so they go to another space, calculate that, say where the time becomes complex, then they come back. I think this happened in cosmology as well. In our universe, the time is moving forwards like an arrow. But when you go to some complex space where the time becomes complex, then the time becomes like static and it's not one thing. So in that case, you can calculate things easier in the complex space where in that complex time space. Then whenever you have finished calculating, you translate the problem, the solution back to our real space. Then you can infer something. I think that is what Stephen Hawking used when he calculated his black hole evaporation theorem. Well, that's nothing to do with this. It's just a methodology that you can always translate something that you want to calculate into something that you know. Then you do it there, then you come back here. So similar here, the first trick is to translate the convergence of a sequence into the convergence of a function. So the second trick is, again, by using theorem, where we use existing rules or existing behavior of some sequence. So I'll tell you that now for this kind of sequence, this is the result. For this kind of sequence, this is the result. But the numbers of results that is happening in the theorem is very limited. And with this theorem, it will help you tremendously to answer the questions of the sequence of n, the limit of n sequence. So for example, here, we're going to have some rule. This rule will help you to pin down a new sequence quite easy. So for example, you have two sequences. You have an, the sequence an and the limit of an exists and it's called a. And you have another sequence bn, and the bn sequence exists is called b. Then if you form a new sequence, say Cn, where each of the term in the Cn is the sum of the corresponding term in An in Bn. So this is a new sequence. So you know that the An sequence converges, you know the Bn sequence converges, then you ask what would be the new sequence An. So answer is that you can got this answer quite easily by using the theorem, which we do not prove. Okay, so this is similar to when we study the limit of functions, right? So we also make use of this theorem, but we don't prove it. Just use it because you know that it's true. So the limit of the new sequence that is formed from the sum of two sequences is just the sum of the individual sequence. Likewise, if you have the difference of two sequences, then the limit of the new sequence, Cn, which is An minus Bn, also converges, and it converges to A minus B. And if you have a two sequence, An and Bn, then you form a new sequence where each term in the new sequence Cn is obtained by multiplying the term an with the term bn, then the limit of cn sequence also exists. It's just the product of the limit of an and bn. So very similar. If you multiply a constant to an existing sequence, then the limit of the new sequence is just the constant multiplied with the limit, and also same to the ratio of two sequence. So with this theorem, you can then generalize it to answer some very simple questions. For example, 1 over n. So first of all, we establish a very simple fact that the limit of a sequence like this, n goes to infinity, uh, exists and its limit is 0. And this could be quite easily seen because 1 over n would drop to 0 when n goes to infinity. So we first establish the fact that 1 over n sequence exists and the limit is 0. Therefore, the limit of minus 1 over n, by definitions, or by the use of the theorem number 4, this is the product of a constant minus 1 times the limit of an, right? So then this, according to the theorem, the rule number 4 in theorem 4, where k become minus 1 as a constant, therefore you write down the limit of negative of 1 over n as a product of constant k times the limit of 1 over n, and you know that this goes to 0. Therefore, this is minus 1 multiplied with 0, and it gives you 0. So that's how you can determine the convergence of a new sequence by making use of the knowledge that the old sequence 1 over n converges to 0. So again, it's very simple, straightforward, but I'm trying to explain to you, when you write down from here to here, from here to here, you are actually making use of the rule in the theorem. Right? It allows you to do that because it's a theorem that has been proven to be true for all constant, including the special case of k equals to minus 1. And again, to do this, you have to then convert the sequence of one. This is what the sequence is n minus 1 over n, and you are asked to see what is the sequence of the limit of an. So to do this, you make use of the limit of the theorem. I think it is what it is using theorem number 2. So what you do is you use theorem number 2 that says if you have the difference of two sequence, then the limit of the two sequence is just the difference of the two limit. So that is what you do. So you try to break this into two parts. This 1 over 1 over n. So that is what you do. Therefore, the limit of 1 over 1 minus n, when n goes to infinity, according to the theorem, to this theorem number 2, it means it's a difference between the two limits. It's a limit of 1, n goes to infinity, minus the limit of 1 over n goes to infinity, and this is 1 minus 0 is equals to 1. Okay, so the limit of 1 over n when n goes to infinity would be very useful. If you have this situation, then you can answer the very simple questions. Let's say n squared. So what is the limit of n squared? So according to the product rule that says if you have two sequence an and bn, then the limit of the new sequence is just the product of the limit of a and b. So in this case, the limit of n squared could be obtained based on the limit of n by breaking down this into the product of 1 over n over n. So now 1 over n has been broken down into the product of two sequence that, according to the theorem I just mentioned, that this theorem number 3, the product rule, then it says this is just n goes to infinity multiply with the limit of 1 over n goes to infinity. Then this becomes 1 over, this becomes 0, 0 becomes. So limit of 1 over n squared is 0 is kind of straightforward. You know about it. But in order to really go from here to here, you have to break down the product of n 1 over n squared into the 1 over n squared into the product of 1 over n and n1 n. Then you apply the product rules according to the theorem. Then only you arrive at here. So You may think that you get this answer quite straightforwardly, but at the back of all this detailed procedure, there is an rule or theorem that allows you to do that. If you don't have rules that allows you to do that, then you can't do that. Okay, so this is just an example. Yeah, so this is very similar to what I said. So if you have 1 over n squared, limit is proven to be 0. So then 5 over n squared can also be obtained. That is like this. So this is just a repetition of what I'm going to write. So if I ask a question of 5 over n squared and goes to infinity, then again you use the product rule for a constant. The product rule for a constant, say number 4. So we are going to use this rule, that is this is equals to 5, where k is a constant, times limit of 1 over n squared and goes to infinity. And now you can say this is equals to 0. The limit of 1 over n squared is 0 because I have just proven it here. Right. So when you have a record of your previous proof, it will be very handy because it will help you to answer this question quite easily. If you do not have this record, then you have to do it all over again. You have to prove it from scratch. So that's why I keep on saying when you do the mathematical proof or calculation, if you know the previous results of some existing results of our existing rules, you make use of that to help you to solve the problem now. Right? If you do not have this record, then you cannot make use of them to help you to do that. So memory is important. It's just like your computer, you have your RAM, you have your ROM. So the memory, if you keep a lot, then anytime when you need it, you can just plug it out and apply it to the current space. If you do not keep this memory, when you need it, then you have to create it from scratch or find it from somewhere. So that will delay the process of getting the answer. So if your mathematics is good, usually you have a good memory of what you have learned before. You can just call out the answer, apply, say, the integration of what tangent is equal to something. Right? So if you can have that memory, instantaneously you will plug it out from your memory and apply. If you do not have that memory, then you have to either ask Google or you derive from scratch. But if you keep on doing that for many times, you keep on recalling that, it becomes part of your memory, then it helps a lot to boost up the speed of your calculation. That helps a lot in your exam because exam is not about just doing the solution. It's about how fast you can do. Because the question could be number, we have 2 hours, we have like don't know how many questions, 3 questions, 4 questions. If you do it slowly, then you would not get it right. So one way to test whether you're good in mathematics is not about whether you can solve the questions, it's about whether you can solve it fast. Now, if you're good, you can solve it fast by calling out the information that you kept in your mind. And that information that kept in your mind comes with a constant practice. Right? Sometimes I think I have a lot of constant practice in the past, therefore I keep all this memory. If you do not spend time to keep this record, that means you don't spend time at all to practice, to keep this information in your mind, and you depend entirely on Google, then this information is not with you inherently in your mind. It's somewhere outside. So whenever you need it, of course, you can always ask Google. But in the case of the exam, you would lose out. And also the memory that is kept in your mind helps to create new idea. Like keeping something information, keep some good information in your mind actually helps to boost up your creativity. If you do not have all this information already kept in that, it has no ingredient, the mind has no ingredient to help you to create new ideas. So having some knowledge in your mind is very helpful to be creative. Right. So, but unfortunately, everyone outsource the information to Google. And they couldn't don't put in their mind. So that could help, well, that could hamper the resource for you to be creative. That's all. I think I have been talking too much. I am wasting a lot of time. I'm not sure whether people are coming in. If people are not coming in, I'll continue to lecture until I finish this part. Okay, sorry, 10:43, and you have been late for many of you have been late for I don't know how many hours. It doesn't matter. So now theorem 3 is a theorem that will help you to answer, well, this is the first theorem. The second theorem that will help you answer the sequence of a function, the limit of a sequence. I'm sorry that I keep having mistakes when I express myself because I think too fast and my speech sometimes does not catch up. So there's the mismatch between what I think and what I say. So I think A, I speak B, and I write C, and everyone get confused. So I apologize for that. Okay, so here is an theorem that will help you to determine the limit of a sequence. So the theorem is like this: if you have a sequence that you know the sequence, that you know a sequence exists a limit. So given the sequence that it has a limit, okay, so then the theorem says this. It says it has to be like this. You start off with a sequence an, and you know an converts to a limit. So you put a full stop there. This is the first information. The second information is that you imagine that there exists a function. So this function is not given, but you imagine it exists, where this function has two conditions to fulfill. So if there is a function such that the function is defined for all values of sequence an. So this is the first condition that this function has to fulfill. Secondly, the function is continuous at L. Where L is the limit of the sequence. So as long as this function exists where it fulfills these two conditions, then the functions at an, the limit, then that means that the functions evaluated at an when n goes to infinity is equal to f of fl. I think that is what it says. Let me say it again. It says if you have an sequence an where an converges to L, in other words, it says the limit of n goes to infinity for an is L. Then if there exists a function f such that the function f is defined for all values of the sequence, it's all defined for all n, and additionally f at L. These are the second condition. L is the number that you know exists. It is the limit of the sequence. Is continuous. Is continuous. Is continuous meaning what? It means that the limit of x when x goes to infinity. I think what it means is that this is continuous. I mean, if you have a function fx and x is tending towards L, then the values of the limit of the function when x tends towards L equals to the values of the function evaluated at L. This is the definition of the continuity of a function at L. Right. So if you can find such a function f, then the theorem says the limit of the function f evaluated at n when n goes to infinity is just equal to f of L. Okay, that is what it says. Okay. Now this is a function, a theorem that is different from the next theorem. The next theorem is very similar, but it is not the same. So here, the what goes into the function is this term an. In the next theorem that we're going to see is slightly different. That is, what goes into the function is the index of n instead of the term an. Now I'll come to that later on. But at the moment, try to understand this, what the theorem says. This is what it says. I've already explained to you. Then you can make use of this theorem to help you to answer the questions. So this is an example.